It's my pleasure to introduce our speaker today, Cristobal Petrovich. Cristobal did his PhD at Princeton University before coming here as a postdoc to CITA. And then he spent a year between CITA and moving on to Católica at University of Arizona as a Bach Fellow. And now he's been a professor at Católica for a couple of years, and Cristobal is an expert in exoplanets and dynamics, and today he's going to tell us about planets and protoplanetary disks. So I'll let you take it away.
Thank you, Sam. Thank you for the introduction. It's been a great week, this one, interacting with people here at CITA. So I've been having a lot of fun. And the thing that I wanted to tell you about today is actually the work that a master's student, Juan Garrido Dudelmoser, has done as a part of a master thesis that he just finished a couple of weeks ago. I arrived to Católica in exactly 2 years ago, and he really wanted to do hydrodynamics and hydro simulations. So it's like, okay, let's try something on the dynamic side of hydro, and let's see how it works. So I'm going to tell you about some possible connection of protoplanetary disk morphologies. When I say morphology, it's mostly going to be rings and gaps and vortices that we can observe in ALMA, to exoplanet architectures. And when I mean architectures here, I will mean multi-planet systems and also resonances, right? So I have to put some of the dynamics in. And this is work that one of them has been published in UpJ, and the second paper, which is the second part of the talk, is about to be submitted. It's been ready for a while, but some of our experts in the team, especially on the observational side, are helping us. Also at Católica, Viviana, at Arizona, and you, Victoria, Rubin Dong, and Kesang, who's been doing some of the gas CO observations. Okay, so let's start from the beginning of the story. Okay, right. So you all know, you're familiar with this image, tracing the millimeter size dust that came out from the ALMA collaboration 2015. We went from something like this, say from the BLA, to a lot of structured rings and gaps, and even, okay. So this is a famous image. I was here my first year at CITA when this came up. And there was also interesting dynamics happening there. Soon after that, there was a large program called the D-Sharp. The D is substructures at high angular resolution, looking at this at roughly 5 AU scaling resolution. And the overall sizes of the Ds are in the order of 100 AU. And you can see non-axisymmetric structures, rings, gaps, in some cases spirals. And more recently, we had another large program from ALMA looking at molecules. So a bunch of molecules. This is called MAPS. That stands for molecules with ALMA at planet-forming scales. Instead of doing 20-ish, like in D-Sharp, they could only do 5. It's a lot of time on ALMA, actually. And what you can see here, this is the 12CO, is that the sources are actually quite extended. And so you see also some of the features here. Probably you can adjust your eye and see that there are also some rings there. So there is a question of whether the dust continuing on the 12CO, the 2-to-1 transition, both you can use it to say something about the disk. Yes, Chris.
That's what the dynamic range is here, i.e. the maximum flux to minimum flux ratio in the top versus the bottom.
I don't know the number off the top of my head, but it's higher here than here. Yeah. And also notice that these are actually 2 different size scales. So the disk and the gas are actually way more extended. The dust tends to concentrate due to dust migration. Okay. Right. So, and as I said, some of the features that people have used with this multi-wavelength and multi-tracer, for instance, looking at the millimeter dust continuum here in gray, you see all these concentric, very beautiful axisymmetric gaps and rings. By looking, for instance, at the scatter light of micron-sized dust, also tracing different scale heights of the disk. You may see spirals, also vortices or crescents, and millimeter light emission that can also tell you about the gas dynamics. And there is a plethora of different things that people have seen, including misaligned disk, large cavities, also known as transitional disk, rings, crescent, spirals, and so on and so forth. There is also a plethora of different processes that people have discussed to actually create some of these structures, including gravitational instability and HD processes. They have different a set of names here that I'm not going to be describing. Tidal processes like flybys from stars, or tidal torques from a planet. Dust processes like ice lines, or the streaming instability, MHD processes, of course, zonal flows. There are many of them. The thermal instability, which would be here in the dust process, I assume. So the question is, what is actually causing these structures, and whether one of our favorite choices, which is planets, we can actually try to see whether these structures come about from planets. Exactly, yeah. But I actually read the review. This is a recent review from Jahan Bai. They mentioned thermal instability like in the dust processes. But I know, yeah. But it's true. So there is the thermal instability and other thermal processes or radiation processes. In some cases, we know these are planets. Yeah, the most classic case and the only case so far, I would say, is PDS 70. This is a composed image looking at ALMA here. You have a sphere, so a scatter light in the infrared, the VLT, mid-infrared. And also you have UV radiation probably tracing H alpha from accretion. So you see the point sources, these are accretion sources. So this would be a system that has been actually confirmed. And so far, I think it's the only one that are claims of a circumplanetary system, circumplanetary disk that may be present, but real detection of planets accreting, and these are fairly massive planets in the order of 5-ish Jupiter masses. There are also indirect probes, just by looking at the gas dynamics and see whether we can trace the motion that a planet imparts on the disk, on the gas disk, not just on the dust. This corresponds, for instance, these are images. This is one of the systems that I'm going to be discussing today. I didn't put the name, but it's HD 163296. It's going to be coming up on the talk a few times. So what you can do here, this is a line emission. You're tracing the rotation. You have the line of sight rotation. You can take isorotation curves, like if we just only Keplerian, azimuthally average that, or see the departures from any sort of a Keplerian flow. So in a paper by Richard Teague and company, they show that there are zonal flows, there are departures from this motion, and those may be created by gradients in the pressure. If there are, for instance, density gaps, they might create a departure from the Keplerian flow, leading to these meridional flows, which are indicated by these arrows. So this is roughly the sketch. The arrows are indicating where this is actually pointing. So you get a lot of, you get the amplitude. I didn't have the figure. So these are, yes, relatively small. So that's why you have to actually average over azimuthally average to bring up the signal. So this is in units of about 20-30% of the sound speed. If you see the scale here. And in some particular cases, if the planets are actually massive enough, and that's actually the work done by Christoph Pinte and company, you can detect also in these channel maps, if you go to an isocurve, you can see that sometimes there is what they call a kink. So there is a velocity perturbation. Otherwise, this would be pretty much circling. You see here that there is a kink. And this is from a model, for instance, using these planic interactions. The density wave is actually creating this structure. So this is another mean to pinpoint to the presence of planets. And in this particular case, there are possibly a few giant planets. And both are actually consistent, either very localized perturbations or more sort of like global axisymmetric perturbations. But direct and possibly also indirect techniques, they depend on the mass of the planets, right? How big the perturbations are, or how bright they might be shining to be detected in direct imaging campaigns. But lower mass planets are actually way more common. For instance, if you take this from radio velocity surveys, this is a paper from Fernandez, I think. You can see that there is a rise in the occurrence of giant planets all the way up to roughly a few AU, and then it falls off again. There are extrapolations, but in principle, we expect that at something in the order of 100 AU, typical distance that we're actually looking at, the rate of giants would be in the order of 1% or less, right? This is also confirmed by direct imaging campaigns, so it's somewhat consistent. So giant planets are rare, especially at these distances, modulo migration, of course. And the frequency, if you look at the microlensing campaigns, tends to actually rise to our lower mass planets. This would be the giants. There is possibly a peak for the Neptunes. This is what we care about is actually there are way more Neptunes than there are giants or Neptune size. So one question that we're trying to tackle here is how would actually Neptunes be inferred in protoplanetary disk observations, if we can. So let me start with some of the work that has been done on this. In particular, you can go to the D-Sharp, and this is work that in the D-Sharp collaboration have done. If you input a planet, the planet is gonna clear its vicinity. This would be a gap opening planet. These are density wave excited at the limb resonances. They travel, they went up, and they clear some of the material in its vicinity. So you get this gap that may be explained in a system like this, SR4, for instance. Okay, that's all good, but this is the dust. Sorry, this is the gas, and we care about the dust. So we have a gap profile like this. We have a giant planet. Because there are pressure gradients, the velocity of the gas is going to be slightly different. You will have a Keplerian beat, but also you will have to be in equilibrium, you will have a pressure gradient. That pressure gradient will actually make, you can follow the algebra here, that make that the gas inside where the pressure gradient is positive, the gas velocity will be higher than the Keplerian velocity. And on the converse, you will have that the outside where the pressure gradient is actually falling, the gas velocity will be sub-Keplerian. That means that a dust grain that is following pretty much Keplerian motion will feel a headwind here. So it will actually drift towards this side, and the contrary happens on the inside, where the pressure gradient is actually positive. So you start accumulating dust at this pressure maxima. So you can do that, and there are a few formula people have studied the gap opening for single planets. They know how it behaves with different quantities. You can compute, for instance, the gap width. It will depend on the mass on the alpha viscosity, H, which is the aspect ratio, meaning the scale height over the semi-mirror axis, and also the depth of the gap. It depends on the same quantities, but it has a different functional form. So we know this actually pretty well. So what some of our colleagues, and a second part that is actually relevant. Oops, sorry. A relevant quantity to think about whether you open or not a gap or how much you perturb actually your vicinity if you're a planet is what it's called the thermal mass, right? So the thermal mass is the mass at which the pressure scale height of the disk equals the Hill radius of the planet. If you follow the algebra, you get to this quantity over here that depends on capital H and A to the third power. And just to give you a reference, if we are thinking about, this is a flare, in principle, a flare disk, this would be roughly the thermal mass for Kepler-like planets in the order of a few Earth masses. Maybe you move out a little, like Chris. It goes up roughly maybe to a couple of Neptune masses. And for wide distances where the disk would be actually thicker in aspect ratio, if we close it to Jupiter. So this is a quantity to keep in mind. And the idea here is that if the planet is actually, its Hill sphere is very small compared to the scale height, it will not really perturb the disk that much.
But at the radii corresponding to the Alma rim, you're talking about the Jupiter mass.
Between these two, yes, yes. Yeah, I'll get to that, please. Yeah. Right. So that's the basic gap opening. Of course, there is a lot of work on that. Shang et al. From the D-Sharp collaboration did go through the process of explaining some of the gaps and rings for all of the ones that here are enclosed. They have different numbers, and folding in uncertainties on sigma, alpha, H, and dust dynamics. They pull out just based on the dust. We're looking at the dust, the masses that you can actually get from this planet interaction. And these are the masses they get. They go from, say, 10 Jupiter masses that are huge error bars because of the uncertainties and all of these quantities, to maybe Neptune masses. So here's Uranus and Neptune. And just for you to get a sense and compare this to the architecture of exoplanets, this is the same figure, but now showing the planets from transits, the planets for radial velocities, these big planets that are the direct imaging ones. Okay, so this is great, although we don't really know what the masses are. And beyond that, there is also the issue that if these are actually low viscosity, a single planet may be able to actually carve more than one gap, right? And this comes about from the non-local deposition of angular momentum. So you clear some of the material, but this is actually being deposited, the angular momentum, somewhere else, not in the vicinity. And this happens in low viscosity disks. This is a paper by Robin Dong, showing here the gas. The gas actually looks very, very smooth, which is the dashed line over here. But if you look at the dust, you need some pressure bumps. It gets these beautiful axisymmetric rings, and more than one for one planet that is actually sitting in a ring. So there is some complication there. So overall, it's hard to constrain the presence of a planet or multiple planets based just on the dust continuum. So you need something else. So we're trying to rely here on planet architectures before getting into the results. And if we're actually dealing with Neptunes, we know, at least from transit surveys, that Neptunes comes in multiples, right? Roughly within 100-day orbits, you might find actually 3. If you look at the period ratio, kind of fine. Is maybe that one? Oh, okay. If you look at the period ratio, This is the Debye-Spiro ratio, roughly following the blue line here. There are many planets that have a relatively compact, tightly packed configuration, meaning that they have period ratios below 2. And this is probably more pronounced at the beginning, before the dispersal. So we know that the period distribution is widening in time because of instabilities. This is true in our solar system. Very weird. Okay. Right, so the current period ratio of Neptune and Uranus is 1.93, but likely before Neptune migrated, or any evolution that you might actually follow for Neptune and Uranus, the period ratio initially was likely below 1.5. So even that was actually compact in that sense. Okay, so I'll be using that. And the question that I will actually pose now is, how could multiple planets or multiple Neptunes can be inferred in protoplanetary disk observations? This is like comparing the case of having just a single Jovian to a couple of Neptunes, whether there is something obvious that comes in the dynamics that you can actually detect and pull out in the observations, right? So potentially just by looking at the dust, you don't know which one it is. It could be just a single Jovian, or you can just have two lower mass planets, slightly comparable to the thermal mass, but because they're two, they open just a wider gap. That's the basic question that we started with. I have a different route in the beginning for Juan, but it turned out to be going in a different direction because I actually wanted to do the dynamics of this, and it turned out that something happened. So let me tell you what happened. So this is the question is, are the gaps separable? Meaning if you have a single planet, this is in now polar, r theta, you open a clear gap. That's a simulation that Juan did, and that may be representative of something like this. Now let's plug another Neptune. So another Neptune, in this case with a period ratio 1.9, you are just open two separate gaps that I would call separable, right? So you can just plug in your formulas, you know, for single planets and put them together, or I mean separate, to the same disk, and you more or less recover the dynamics. And it would represent something like this in the observations. And these are simulations that have been done with a Fargo 3D from Pablo Benitez and Bay, who is also now in Chile, and Fred Massin. Right, so now if you play the game of getting the planets closer and closer, the question, what happens? Right, so we started here. This is a single planet. You just have this very clean gap. You have the two planet cases. Here's the surface density again, two relatively smooth gaps. We have separations here at the point of roughly 11 Hill radii apart, and we start getting them together. You can see, sorry. Okay. As you can see, I've been very busy at CITA. So this is some of the transitions haven't been polished. Sorry about that. Right, so if you get the planets actually closer and closer from 11 Hill radii, 8.8, 7.2, and 4.3, something happens. This is after 5,000 orbits in the hydro simulations. So this is actually million-year-old sort of these are million-year-old systems and for millions of orbits in this case, for fiducial values. So what happens is that when you get actually close enough, the ring that separates the planets become what is called Rossby wave unstable. And you create a vortex. So this is a vortex. Here I'm plotting the Rossby number on this column defined here. And what you can see, especially the things that are actually encircled in green, those are strong vortices that have Rossby numbers below 0.15. There is a sort of family of vortices, but this would be actually a very strong vortex. This one too. And if you get them actually even closer, you transition from having a vortex in between the planets to having a crescent at the Lagrange points that you can observe over here, right? So this region in particular, it also has some vorticity. It also resembles a vortex, but this is actually fairly dynamic. So it's very hard to tell. And this would be the azimuthally average profiles, right? So it's definitely not separable, right? So if you take, for instance, the dashed line, which is using some of the recipes we have from simulations to get the profiles of these density gaps, especially in the vicinity of the, is not going to really fit. Actually, the problem is totally non-axisymmetric. And this actually lasts for, we have tried this for 10 to the 4 orbits, and it still remains there. I'm going to get to that because I'm going to show you a bunch of simulations. All of these are roughly thermal, below thermal, subthermal, but within a factor of 2 or 3.
So thermal roughly. So the other question I have is that the mass of the, when you open the second figure, the second, right? What's the mass of the gas in between the two planets compared to the planet mass?
Right. So this particular set of simulations, we're just looking at the gas dynamics, not the planet dynamics. Therefore, we're artificially lowering the surface density so the planets don't migrate. We're actually changing that. So we actually increase the surface density, the planets do migrate, and you don't have like a very clean test here.
Even before the migration, is the gravity from this gas more important than the two planets gravity?
That's what we're actually trying to see now, especially with dust. But the important thing is that it's very like dust trapping. So it might actually become like its own massive entity. And gravitationally can actually matter, but we haven't done it quite yet. Yes.
Well, of course, if you want to, then just in between them and on either side of it, we'll have other bodies in it. I mean, it's not going to just be planets and dust, surely, right? I mean, there could be a mass spectrum.
You're thinking about the dust.
Oh, I'm just thinking about the planetary material, right? You put in 2 planets, but they don't appear from nowhere, presumably.
Oh, sure. Yeah. Yeah, this is assuming there are planets. This is what happens to the gas.
Yeah, I guess my concern is the planet came from only the solid material.
Mm-hmm.
So majority of the material is there, which is gas. So
Right.
90 degrees that gas products will have.
Yes. That's what I think so too. But yeah. But in this set of simulations, at least, we're dealing with a very low surface density to not care about migration.
No migration because gravitation.
Yes. Yeah. Mm-hmm. Right. So this is the behavior. We have a classification of regimes. Regime 1 is when you have a vortex in between the planets. Regime 3, we call it whenever you start accumulating material around the Lagrange points. There is another quantity that actually matters a lot, which is called the shock distance. So the way this non-local deposition of angular momentum is like a wave steepening process. This is a theory that has been developed partly by Jeremy Goodman and Roman, where the wave steepens, breaks, and deposits the angular momentum. So even if you have 0 alpha, you still have some effective alpha just because of the turbulence that you create. And for low viscosity disk, like the ones we're dealing here, so alpha 10 to the -4, not crazy low, but still relatively low. This is the time scale, this is the scale distance that actually matters if you want to start classifying things. You can see here where the vorticity perturbation, it roughly peaks at this shock distance, right? So this is it's been visited a couple of times more recently by Zimmerman and Rafikov. So that's going to be the relevant distance scale. For the Lagrange points, which is the regime 3, those are the regions that take the longest to sort of evacuate the corrotational material. Of course, this depends really on the alpha, but for low alpha models. So if you compare, for instance, a single planet, you have that the Lagrange point number 5. This is the contrast between the surface density at the Lagrange point relative to the background. And as you can see, it decays away if you have a single planet, but it becomes actually very time dependent and variable when you have two closely packed planetary systems, just because they have density perturbations and vorticity perturbations between them. And in principle, it actually survives more than 5,000 orbits. So just by, we try to find a way of classifying the different regimes you might find with the different parameters. This is a busy figure, but again, the classification is 1 is a stable ring, 2 is a vortex in the ring, and then Lagrange 5 and 4 vortices. This is the mass of the planet in units of thermal mass, and this is the spacing between the planets in units of this shock distance, which is the natural distance you can use. And you can see that by pretty much changing age, mass of the planet, spacing, and so on and so forth, with 40 simulations, you can actually separate them actually very well, right? So the ones that are more spaced together will have this ring that is stable. In between, you will have the regime 2 with a vortex in the ring. And if they're very, very close to each other, they have these Lagrange points. And these are just empirical fittings. But in reality, actually, the dependence is fairly weak if you do the math. And as a rough value, if the spacing between the planets is above, say, 8 pressure scale heights, you don't have any vortex. If it is below, you could be either in these two regimes with a break at 4.6 pressure scale heights. This is just preliminary work doing migration. So this is the similar figure that I showed before, 500 orbits about till 5,000. Of course, since the planets are getting actually in this particular case closer together, this is the period ratio, you're transitioning from, in this figure, from being somewhere in here to being closer to this other regime, although we haven't really gotten yet. We wanted to see if there is any transition. But as you can see, the vortex actually survives the migration, right? So this is up till 5,000 orbits. But this is still work in progress. And there are many questions you want to actually raise here, that it has to do with how does the damping of eccentricities behave now in the disk-pranic interaction theory? If you have a vortex in between, how does convergent migration actually behave? And all of this nice stuff for dynamicists like myself. So this is still work in progress.
Now, what's the mass ratio of the two planets?
If I have changed it?
Yeah.
Is it still, yeah. Oh, to be divergent?
Well, yes.
Yes. I think the dynamics, at least from the vortex perspective, remains the same. But at some point, it will, if it is divergent, you will lose the vortex. But yeah, we should do that definitely carefully. So there is some more work to be done there. Okay. So the final question, if you want to tackle and compare these two observations, is to ask, what happens to the dust here? I have only talked about the gas. So now this is a Cartesian model. This is actually tailored to Neptune and Uranus. So this would be like an early Neptune-Uranus with a period ratio 1.7, which is kind of surprising that it could be, in principle, still be detected, assuming these values, of course, of the disk. Scale aspect ratio 5%, alpha 10 to the minus 4. In any way, in this particular, the 1 millimeter dust particles do actually show up very clearly in the crescent that has this vortex, which is good. Okay, so the takeaways at this point is that we show that compact subjovian mass, I've been calling these Neptunes, in low viscosity disks create both like shallower gaps for a given width compared to a single jovian, just because they have lower masses, and long-lived vortices inside the gaps if the relative spacing is below 8 times the aspect ratio. To convert these to period ratios, it has a very weak dependence on the mass. So if the aspect ratio for most of the reasonable aspect ratio for this disk, maybe not for Kepler, which might actually, the Kepler planets might be thinner inside like 1 AU, planets around the 3-2 resonance should actually show these vortices. If you somehow get trapped into these resonances, they might actually show up as dust trapping vortices. In the future, we want to deal with a planet migration, the effect on the vortex, and also the back reaction on the planets, and study compact structures. So something I haven't mentioned is that sometime in some regimes, the aspect ratio of the vortex is in the order of like 2. So it's no more like a crescent. It could actually look like a point source, right? So that has implications for searches of a circumplanetary disk, for instance. Okay, so in the last 10 minutes, how long? Yep. 10, 20? Oh, okay. I will apply this. So this is part of the second paper. We try to find a system where it's actually showing up currently what we're proposing, a set of compact, a pair of compact planetary systems. Right, so the system is exactly the one that I gave you, showing the introduction, very conveniently. This is one of the best studied systems so far in ALMA, right? So what I'm showing here, again, just to remind you, is the dust millimeter continuum, pretty much at the midplane. We have the 12CO, the one in the box here. It actually encapsulates this whole box, right? So it's way more extended in the gas, right? So people have already given hints that there might be planets due to these velocity kinks. I'm repeating myself from the introduction. And these are either the velocity kinks or these meridional flows. And also these are roughly consistent, and this is a tricky statement though, with gas gaps. So far, these are only dust gaps. And the question is for HD 163296, whether it coincides after modeling this disk, which is work that it was led part of the MAPS collaboration by Coco Sen, who is one of the collaborators in this paper. So she's been helping us to make sure we're doing the comparison right in the dust and in the gas, sorry. So by doing that from the paper by Shang, they observed that initially, yes, there is some coincidence here between the dust, which shows in this dark blue, and the gas, which shows in this light blue. There are some issues here. There are also a CO ice line, I think roughly at 770 AU, but we're actually focusing mostly on anything that is inside 60 AU, where that problem actually shouldn't exist. So what do you spot in this figure that is kind of unusual? Do you see it? It's just me. There is a crescent. Do you see it? Or I got convinced after looking this for way too long. I'm a believer now. So there is a crescent. And one of the proposals from last year, from Roderke and others, was that maybe this was actually a Lagrange point from a giant planet. So a giant planet is opening the gap. This is the observation again. And this is the simulation after 2000 orbits. But this is just a single planet. So it's a single Jovian opening the gap in the dust and creating this crescent, which is the Lagrange 5. It's hard to see that is the Lagrange 5 because this is actually the inclination is like is retrograde, so it's spinning in the other direction. So, but it's a trailing point.
That simulation, is the planet also around?
No, they use the other, right. So thank you, Chris. They use the other planets that have been constrained from kinematics. Yeah, this is a 3-planet model. They have one planet here, which is the cross, and they really focus on this one. There is other one here, and there has to be another one carving out this other gap. Yes, there are 3 planets here, but we're mostly interested here on the crescent. And one detail, of course, I mean, one obvious thing that is going to happen if you have just a single planet is that if you put the planet at the center to have a center gap, the simulation will give you a crescent that is exactly at the center. So and you see it from the observation, and again, this could be just me convincing myself, but this is actually off center, and people have actually measured this in more detail. Right, so there is some offset of the vortex, or the that's a very good question, and the answer is we don't know, and people haven't really explained this. I think it takes a little bit longer to deplete the material, but I haven't seen any work explaining why there is this asymmetry. People have seen it in the simulations. In our simulations, I will show you, we see both, actually. One really shows up, and the other one is weaker. But you might actually, you start with 2, and one actually lives longer than the other one. Right, so if this wasn't a 2000 orbits, you would actually see both. So yeah, so you can make actually many choices there. And the problem, which I think is more drastic than the offset, is that if you just put a single planet, you will carve a deep gap. This is a giant planet, right? So this is just based on some modeling of Coco, of her maps paper, showing that if you compare the CO gap that is actually measured, the contrast is in the order of just 0.5. So you really deplete it at most by a factor of, say, 2. However, if you put a giant planet that predicts the gap in the dust, the depletion becomes more than an order of magnitude, right? So this is something they pointed out, and we saw this with Juan. It's like, okay, let's try to tackle this. It seems to have actually all the ingredients we need to actually do our modeling, because our model is already predicting shallower gaps. So let's see how it behaves. We're comparing a single Jovian to 2 Neptunes, or super Neptunes. You got the first part right, so this is the surface density. You can see that there is a big difference between having just 2 for the same width. We're getting exactly the same width. You get a much shallower, roughly exactly a factor of like 2 in depletion. So you might actually be getting that part right. And this is where we compare with the CO gaps in the maps data. And this is what they help us to do actually the same procedure, just post-processing this simulation with the same bin size. And we're comparing the black one to the 2-planet cases, which is here in orange. And more or less the depth is, let's say, well reproduced. And Jianxin looks skeptical. Okay. So there is some modeling there. Yeah, and you are actually looking at high altitude CO, right? So it's not at the midplane. We're not. Exactly. Yeah, I agree. Yes, yes, and that's what the paper of Coco was about. Try to do the full sort of like modeling with the vertical structure to back out the column density in the gas. But yeah, it depends on the model itself. Yes. Mm-hmm. Mm-hmm. Right. Okay. So leaving aside those issues we don't tackle. So that's why we call the expert here. the observer. With two gas giant planets, it's actually, with the BINA now, it looks less severe, but it's still off. So that's the gas. So I think we have one check here. And the other one is looking at the dust. Now we're putting 4 planets. So we have one planet creating the outer ring, shaping the outer ring. We have planet we call 3 here in between these two, and planets 1 and 2 that are creating actually this vortex. This is the image in ALMA. This is the observed post-process image. And for me, it actually looks very well. We haven't played around with the parameters. I have to, yes. But there is, of course, a lot of machinery here that Quan did, like the dust distribution in 3D. There are assumptions about that. Radetich transfer with the Monte Carlo, the RAD-MC. And there's a template actually for this system to consider the properties of this disk in ALMA. But maybe more transparent than just comparing these two, which I think we all agree this is actually pretty amazing fit, or I'm still a believer. But the dust species, if we go from, say, highly coupled to the gas, very small one, to not so coupled at the almost 2 centimeters. So the ALMA band 6 is roughly looking at this one. So without post-processing, you see that it shows up in the data, this crescent, and is the Lagrange 5 point of the outer planet. It actually survives for a very, very long time. We're now trying this with migration and seems to be okay. Also, as Renu was pointed out, why it doesn't show up in some other Lagrange points? It does, but it's weaker. Maybe you go to like these very large grains, if you can call those grains. These are centimeter. You see here a Lagrange point also of the other planet. So potentially there are 4 Lagrange points. But the most prominent one, sort of a time average sense, is the outer planet and the Lagrange points of the outer planet. But as I showed you before, this is very time variable. So this is, for instance, how it evolves in time. You see that sometimes the dashed line is the Lagrange 4. It's actually above the Lagrange 5, but for the most part, the Lagrange 5 is. We don't have a good sense. We're trying to put some particle tracers to more or less understand the dynamics. Okay. And finally, dynamics. Surprise, surprise. Our best model, and actually you can do it just by taking the image from ALMA. If you put up the rings, this is not numerology. Our best model is near commensurabilities. I wouldn't trust the first 2 planets, but if you take planet 2, 3, and 4, they're all near 2 to 1, and very near 2 to 1. And you can actually do it just by looking at the image. You can just see the sizes of the rings you put in between. And also from our simulation, they're all roughly near 2 to 1. The inner pair is very close to 4 to 3. So we asked the last question on this paper, which is, may have been migration actually shaping the orbits of these planets, right? So could you actually capture the planets into these resonances, and whether you can actually learn something about it? So what we did is to take some of the migration rates just by looking at the surface density at the locations of the planets. This is from the observations. The planets we used, you see that the masses are actually fairly large. So these are not actually Neptunes. These are sub-Saturns, but the mass of the star is 2. So they are in the regime of being roughly a Neptune. And the migration timescales are all roughly comparable, just by looking at the data, in the order of millions of years, a couple of millions of years. The star is 4 million years old. So the numbers seems to be somewhat consistent. I wouldn't trust these numbers very much, but in principle, there is nothing odd with convergent migration. If you look at this, the outermost is migrating faster than the innermost if you take these numbers. So in principle, if you just plug in the formulas for type 1 kind of a migration with some taking the density at the gap, at the minimum of the gap, you get convergent migration. So we use just these parameters. And indeed, we get the outer, these are the period ratios of planets 1 and 2 that engage in the 4-3, although we had to start relatively close, just because there is not much. Yep. Chris.
Planets open gaps, you just can't apply the type 1 formulae anymore.
Say that again, Chris. Sorry.
Open gaps, then you need to know about the viscosity of the disk to work out the migration.
Yes. Some of the recent papers show that at least in the case where you have shallow gaps, which we do. If you go to one of the figures before, these are the gaps. These are the ones in red. These are not like really deep gaps. So it's still a modified type 1 migration, Lindblad-like. Yeah, Kanagawa and others have formulas for that. And you effectively just replace this by the surface density at the bottom of the gap. Yeah. But I wouldn't trust these formulas too much. It really matters evolving this all together. So it's this is just to give you a sense. So this is using a rebound. I should have cited rebound here. Hanno will complain. But I think at this point it's just the default. So more or less. Right, and when you can see that indeed the planets, they have to start though very far out, 400 AU, and you might have complaints about that. Though the disk goes all the way up to like almost 1,000, so 800 AU, something like that. If there are convergent migration, you get into commensurabilities. The dashed lines are the current positions. You get some of the eccentricities excited, but not to very large values. And you engage into two-body resonances in this particular case. This is between the planets 1 and 2, near 4-3, planets 2 and 3 at the 2-1, planets 3 and 4, 2-1. And then what I think is actually more interesting for the perspective of trying to go and find this planet, if it is possible somehow, or just looking at different dust components that might accumulate in some other of the Lagrange points. We have the three-body resonance, right? So this is just depends on the mean longitudes, lambda. So you have these combinations of angles, meaning this actually depends on where the planets in their phase are. Not exactly, because there is some eccentricity. So you can compare from here to actual position angle. And because the orbits are somewhat eccentric, you get a wider amplitude. So that's kind of a subtle point, but this is what you get in the position angle, which is kind of interesting. So if you know the position of one and the position of the other one you know planet 2 in principle, because you know that it's 60 degrees away from the crescent. You know planet 3 because of the kinks in the velocity. So you can predict where planet 1 is and where planet 4 is using these two angles. This is still work in progress. This is actually very subtle to get all these resonances. We haven't played around with this. We just use the fiducial values, but it looks promising. Okay, so the takeaways from this part, this application, two subsaturns inside a dust and gap dust reproduce the crescent remarkably well. The axisymmetric dust rings and gaps too, and also what is being observed in maps, meaning shallow gaps in the gas. And our global model, a 4-planet model, is consistent with being part of a long resonant chain, the inner pair of 4-3, the outer 3 in the Laplace resonance chain. And it more or less connects to wide orbit exoplanets. So if you look at, for instance, this is a very famous one, HR 8799. These are 4 giant planets. The more recent modeling, they show that these are actually, this is the same spatial scale. So we cannot really compare this to Kepler planets, but just wide orbit planets. And you can see these directly imaged planets. It's a famous one, maybe in a long chain of 8-4 to 2-1. So there might be something there. Also, if you look at the other one that is being discovered, and of course, this one has no gas in it, right? But it's still a relatively young system. And then PDS 70 that has two. They've been shown that also is in a 2-to-1. They might be in a 2-to-1 resonance, or it's consistent with being in a 2-to-1 resonance. So, are there systems where you can actually apply this and where to find? Meaning, trying to find inside the gaps structures that actually point towards the presence of planets. There was a very recent paper by Feng Long. It appeared a month ago, showing this image. This is again ALMA in the millimeter, La calcium 15. They show that there are these two features, Lagrange 4 and 5. They claim that this is actually material co-orbital to a planet. They haven't really done much of the numerical exploration yet, so they actually use some of the old simulations, and they claim that this is actually a Neptune-ish mass planet. Well, 2 Neptune masses roughly for these parameters. But they just put just one planet, and we know that one planet, all of this material actually decays with time. It's not sustained. And also, you see that there is a lot of gas and dust inside, where the image here is very much carved out. So by necessity, you need to implant more planets and see how the dynamics of multi-planet systems could in principle shape this. Okay, and also there are some colleagues in Chile working on another system that seems to be promising for the other regime. So far, this is just co-orbital material, Lagrange points, but we haven't seen any that it may be consistent with the ring becoming Rossby wave unstable, and we might actually have one soon. Okay, so I'll leave a summary. The vortices inside, Chris is getting ready to applaud. Vortices inside gaps exist when the interplanetary separation is below roughly 8 scale heights. You have this classification of stable rings, vortex inside the rings. Our proposal for HD 163296 reproduces most of the features we observed. And in the future, we want to apply this to orbital migration, see the effect on the vortex, the back reaction on the planets, and hopefully apply this in principle to other systems. Thank you. So I can take any questions.
Thank you. We have some time for a few more questions. Anybody in Chris or Taylor?
Thanks, Cristobal. I had a question about I'm wondering if you were able to map the vertical scale. Because I'm just thinking you have so many planets embedded in this that you're going to be stirring up sort of the gas and dust in plane. And observations have shown that the vertical scale has large dust, and it's like very, very small. And so I'm wondering if your planets are stirring that up, or if it's like roughly consistent with those properties.
We don't know from the simulations. I agree with your statement. We're just, I mean, this is fairly large dust, so it's probably in the mid-plane, but we don't have anything to say just based on the dynamics of planets on the dust for puffing that up just based on gravity. That's a good point. Yeah.
Thank you.
I guess I'm just curious. So as you are clearing that gap between the planet and then you induce a vortex, I guess there's a lot of angular momentum transfer from the disk into the planet. So I guess can you make some connection between the angular momentum of the planet and the architecture and the disk somehow? And could that be a potential?
Right. So the way this operates is indeed changing angular momentum through these density waves, right? So you have an imbalance sometimes between the amount of angular momentum flux that is going inside and out, and that causes the planet to migrate. You create a torque. We haven't really studied that in detail just because We wanted to have a cleaner problem where the disk is very low mass, so it doesn't back react on the planet. But this is something that we have to really tackle, right? So it is a numerical problem for the most part, because if you put the planets in a very massive disk, they just migrate too quickly. This is known as the problem of migration, right? So if there is an imbalance between these two torques, things actually happen in timescales that are very short. Chris.
So, excellent. Thank you, Cristobal. Have you thought about the steady state criterion for the vortex that forms with regard to its gains and losses of angular momentum and vorticity? You have these spiral shocks running into it and depositing both, and it has to be in steady state over long periods of time. So how does that work?
Yeah, I thought I had a figure for that. We have thought about it. There is an effect of having the planets effectively they have this spiral waves traveling, and the picture looks more like a top sometimes. You start spinning it because there are two waves passing each other and creating this sort of anti-cyclonic motion. So we see that from the simulations. I thought I had a figure, but I don't have one. So this is the closest figure you may see. This is the Rossby number as a function of time. There is no steady state at all. This is the cross marks the position of the planets. So this is radial. Sometimes you have an M0, you have an M3, M2, and they evolve, they merge with each other. It's actually fairly dynamic. I'm not sure if I'm responding to the question, but Chris.
The vortex to small eccentricity in the planet's orbits.
I have a hard time.
How sensitive is the vortex to small eccentricity?
Oh yeah, that's a great.
Small
Oh yeah, they have some eccentricities, the planets, and the order of 1% though.
When you're doing the height though, are you assuming circular?
No. They're allowed to move freely. Yes, and feel the gas and feel the vortex. The thing is that they feel barely anything because it's low mass. But that's exactly what we're trying to do. Yes. But it definitely has an effect. It might, yeah.
Well, I mean, this comes up, of course, part of the
Yeah.
Last question.
What's the compelling reason for you to have 4 planets in your model? Is that a minimal model, minimal number of planets?
We're really focusing on so we try to isolate the problem initially and just have the 2 planets and focus on the region where you have the crescent, because that's what the paper is about. However, for reasons that we don't understand, so I'm starting to encounter problems doing hydro now. I'm used to dynamics where I can actually understand things very well. Here it's a little bit, it's too nonlinear. It's free to actually get the vortex to work for a long time for reasons we don't understand. We try to isolate it. Yeah, so we try to come up with a minimalistic or minimal model for this region, and it wasn't very successful. So we just relied on previous works, like the work by Roderkeefe and some others. So yeah, but that's a very valid point. It just relies on the presence of these other gaps and the fact that there are velocity perturbations that indicate the presence of the planet. Yeah.
Great. I'll do one last call for questions online, and if there are none, let's thank Cristobal one more time, and we can retire upstairs. There should be some refreshments and stuff.